Hi, so today we are going to talk about the counting algorithm. So, quantum counting. And last time we had seen that we had a classical algorithm to count the number of marked elements. And we saw that if I want to do to count the number of marked elements in a database with high accuracy and with high probability, we need order of n queries classically. So today I'm going to talk about a quantum algorithm that reduces the number of queries to square root of n queries quantum. Okay. So the idea is it's quite simple. If you look back at the Grover's algorithm, right? So you have in the Grover's algorithm, you have um, a two-dimensional space, which looks like this, right? So we have psi s perp and psi s. And then we have our initial vector psi, which is the uniform superposition vector. And we have this angle theta over 2. And each iteration of the Grover search shifts the vector psi towards the solution space. So this is G psi. And we have this relationship between m and theta to be this. So square root of m over n. So this is the crucial relationship. Now we also know that we have eigenvectors and eigenvalues of the Grover operator when it is restricted to the two-dimensional space. So the Grover operator restricted to the two-dimensional space looks like this. So this is minus sine theta, and cos theta. And this is a rotation operator. And the eigenvalues, the eigenvectors of these Grover operator are e to the I theta alpha 1 and g of alpha 2, where alpha 1 is equal to 0 minus I 1 over square root of 2, and ket alpha 2 is equal to 0 plus I 1 over square root of 2, where 0 is referring to this vector and 1 is psi s in the two-dimensional space. Right. So the idea is that we run a phase estimation algorithm with the unitary to be G, and then estimate theta and use this relationship to estimate S. So the idea is two-step: estimate theta by running a phase estimation algorithm with U is equal to the Grover operator, and then use relationship between theta and m, which is given by this equation, to estimate m. And it turns out that we can reduce the number of calls to the Grover operator to basically 2 to the power n over 2. And so that is going to be square root of n calls to get a good estimate, and that will reduce the number of queries. Okay, so let's look at the circuit. So quantum circuit. So we have the top registers to be just like the regular phase estimation algorithm. We have this Hadamard tensor T, this is 0 tensor N. And then bottom register, we have to use we are going to have n. So this is, sorry, this is going to be t. And over here, what we are going to do is, instead of passing this eigenvector, alpha 1, ket alpha 1, we are going to use the relationship between psi and alpha 1 and alpha 2 to be theta over 2 alpha 1 plus e to the minus I theta over 2 alpha 2 over square root of 2. So since this vector is related with these eigenvectors in this manner, instead of passing alpha 1 or alpha 2 in the phase estimation, we are going to pass the uniform superposition vector. So this is going to be in the bottom. So this is going to be ket psi, because it's easy to construct. And then we are going to apply the Grover operator. So this is going to be the Grover operator, just like the regular phase estimation. And then, of course, we have the control. And then finally, we have the measurement. And over here, we'll get an estimate of theta. So this will be some estimate of theta. Now, the accuracy will depend on the number of bits on the top register. And the so if it turns out that if we choose t to be nearly n over 2 plus some constant, then we get an accuracy of then we get an accuracy of 2 to the n over 2, which is sorry, we get an accuracy of square root of m. And moreover, the number of Grover operators that are get applied, which is the number of calls to the database, will be 2 to the n over 2. So this is accuracy, and this will be the database calls. So this will be database calls, which will be square root of n. Okay, so the idea is to choose t wisely, and it turns out that n over 2, approximately n over 2 bits are sufficient. These n over 2 lead to 2 to the n over 2 calls to the database, because that will be the number of Grover operations that get applied. And one can show that this leads to an accuracy of square root of m. And this analysis we'll see in the next video.